Today's notes are all about graphing compound inequalities. We should start by defining what a compound inequality is. A compound inequality is two inequalities. Typically it'll be two. Everything we do will be two, but you could have more, two or more inequalities connected with an and or an or. Two or more inequalities put together with an and statement or an or statement. If we have an and statement versus if we have an or statement, we are going to handle them in different ways. So let's talk about and first. In order for an and statement to be true, we have to have both statements true. And, I think we all know, means the word both. So for an and statement to be true, both statements must be true. Both inequalities must be true to make the entire inequality true. For an and statement, we are looking for where both inequalities are true. So again, we are trying to find where both inequalities are true. That's where we want to shade in, is where both of them are true. Which means if we were to look at the two inequalities graphs individually, we would shade in the overlap of the two inequalities. Because I need both of them to be true, we look at the first one, we look at the second one, and then our final answer, we want to shade in the overlap, where both of them are true. So again, a compound inequality is two or more inequalities. They'll be connected with either an and statement or an or statement. The word and means both, so both statements must be true to make the entire statement true. We are trying to find where both inequalities are true, which would be the overlap of the two inequalities. That is where we're going to shade in for an and statement, is the overlap. For an or statement, or means either one. Either statement can be true to make the entire statement true if it says or. Way up here we use an or, two or more inequalities connected with an and or an or. It doesn't have to be both, it could be either one, right? So an or statement, either one could be true, making the entire statement true. Which means because we want either inequality to be true, the first one could be true, so we shade in that inequality. Or it's possible the second one is true, so we shade in that inequality. So when we graph an or statement, we are going to shade in each inequality. Shade the first one in, shade the second one in. So let's take a look at what we've got here. Example 1 asks us to graph each compound inequality. Graph each compound inequality, and the first one that is given says x is greater than 5 or x is less than or equal to 1. X is greater than 5 or x is less than or equal to 1. So we need to make sure we have 1 and 5 both on our graph. And for an or statement, it's said to shade in each inequality. X could be bigger than 5. So if x is bigger than 5, the whole statement's true. So I want to shade in everything bigger than 5. X could also be less than or equal to 1. So we need to shade in everything less than or equal to 1. all of the numbers that I have shaded in are either bigger than 5 or are less than or equal to 1. For an or statement, we shade in the first inequality, we shade in the second inequality. Either one could be true to make the entire statement true. Second one looks very similar. X is greater than 5, or notice we flip this symbol around. Now it says X is greater than or equal to 1. X is greater than 5, or X is greater than or equal to 1. Everything greater than 5 needs shaded. Or X could be greater than or equal to 1. Everything greater than or equal to 1 needs shaded. Including that 5, whoops, greater than or equal to 1. Notice I'm shading everything greater than 1, including the 5. The 5 had an open circle, but when I shade everything greater than or equal to 1, it gets filled in. I have shaded everything that is either bigger than 5 or greater than or equal to 1. Another or statement, X is greater than 2, or X is less than or equal to 9. X is greater than 2, or X is less than or equal to 9. For an or statement, either one can be true, so we shade in each one. We shade everything bigger than 2. Or X is less than or equal to 9. We shade everything less than or equal to 9, including the 2. All these values over here are also less than or equal to 9. Notice I wind up with my entire number line shaded in this time. We could say all real solutions. Every number, if you think about it logically, every single number is either bigger than 2 or smaller than 9. Every single number. Let's do one more or statement. Looks like we need to go down to at least -3. I'm going to label every other one. It's an or statement. We shade in the first one. X could be less than -3. Or X could be greater than 0. Again, for an or statement, we shade in the first one, we shade in the second one. We shade in each of them because either one could be true. It could be the first one, it could be the second one, it could be both of them. Let's move on to and statements. So example 2, again, we are asked to graph each compound inequality. And this time we have and statements. X is greater than 2, and X is less than or equal to 5. Remember, and means both. So I need both these things to be true. So I'm not going to draw on my number line yet. My number line is where I'm going to put my final answer. But up above the number line, we're going to do a little bit of work to help us get the answer. So we need X to be both greater than 2. So up above the number line, let's graph the ones that are greater than 2. Open circle, shaded to the right. And I also need X to be less than or equal to 5, which would be a closed circle on the 5 and shaded to the left. And I'm looking for where both of these things are true. Notice over here, just the bottom one's true. I just have the bottom one shaded in. And over here, I just have the top one shaded in. But in between 2 and 5, I have both of them shaded in. So we're going to bring down our open circle. It's an open circle on 2 because the bottom one is true, but not the top. They're not both true at 2. They are both true at 5, so I bring down my closed circle. And everything in between is where they are both true. So again, I'm using the top here as kind of checking my work. And remember it said for an and statement to be true, I need both to be true. I'm looking for where both of them are, the overlap of the 2 inequalities. Let's try another one. X is less than 2 and x is less than or equal to 5. X is less than 2 and x is less than or equal to 5. So again, up above, I'm going to graph x is less than 2. It would look like this. I also want x to be less than or equal to 5, which would look like this. And I'm looking for where both of these things are true. You'll notice over here, neither one of them's true. In between this time, the bottom one's true, but not the top one. They're both true over here to the left of 2. So on my number line, again, I'm bringing my open circle down. 2 is not part of the solution because it's not part of the top solution. And I need it to be true for both of them. So I have an open circle at 2, and the overlap was to the left of 2. This one says x is greater than 1 and x is less than -3. So we'll make sure -3 is on there and 1 is on there. Again, with an and statement, I need both to be true, so I can't shade in anything on the number line till I think about what each of these look like. X is greater than 1 would look like this. X is less than -3 looks like this. I need both of those things to be true. Notice there's no values that are both bigger than 1 and also less than -3. This one has no solution. You can leave your number line blank if you're asked to graph it. If you want to write no solution next to it, that wouldn't be a terrible idea. Again, if you think logically, which values are both bigger than 1 and also less than -3? There's not any. No solution. And statements sometimes are written like these with the word and in between, but probably even more often look like this, where it's one inequality, the x is in the middle. This means x is bigger than -3 and x is less than or equal to 2. So we can put our number line out there. X needs to be bigger than -3 and also less than 2. These are the values in between the -3 and the 2, which makes sense that the x is in between the -3 and the 2. So we've got an open circle at -3, a closed circle at 2, and our shading is in between. If you wanted to do it where we drew up above, notice the x is bigger than the -3. The x is smaller than the 2. And notice our overlap of those 2 is in the middle there. Example 3 is one for you to do. I want you to try these 4. You can pause the video. Everybody in the class try it. Once you think you have them, you can play the video and it'll show the solutions. This one's an or statement. Or statements mean either one could be true. So x could be less than 7. That should be part of my solution. Or x could be greater than or equal to 11. That should be part of my solution. Final answer should look like that guy. Second one here is an and. For an and, I need the overlap. If I'm looking for the overlap, this is when we draw a little graph up above and see where they cross. X is bigger than 6, looks like that. Less than 10, looks like this. The overlap in between. So close circle on the 6, open circle on the 10, shaded in between. This one's an or. Remember, for an or, either one could be true, which means I shade in both. X could be less than 5. I want everything less than 5 to be part of my solution. X could also be less than 10, and everything less than 10 needs to be part of my solution, including the 5. Final answer should have an open circle on the 10 and everything to the left of 10 shaded. Oops. -2 as I get bigger, -1, 0, 1, 2, 3, 4, 5, 6. X is between -1 and 5. Close circle at -1. Open circle at 5. Shaded in between. I want X to be bigger than -1 but smaller than 5.